Thank you, Peter, for the very kind introduction. Can you hear me well? Okay, great. Yeah, just to say, the Gemini, this is a really big team effort with many people contributing. So just to say, like, I do contribute a very small part, but it's a very exciting project. So if you haven't tried Gemini, especially multimodal capabilities, do give it a go after this lecture. Okay, so then without further ado, I'll talk today about vision language models. And this is a very big topic. We have roughly an hour or so to cover this. We'll start easy and then speed up. And then at the end, we'll have some breathing room again where we'll look at some upcoming things. I have a bunch of slides, but feel free to ask questions during the presentation. If something is unclear or if you want more information, please raise your hand and I'll come to you. I'll also be around for the rest of the week, so probably until Friday afternoon. So feel free to, if you see me around, just bug me with any sort of questions you might have about VLMs or DeepMind or Oxford or Zurich. Okay, so let's get started. As I mentioned, this is a very broad topic, a lot of things to cover. So to give it a bit of structure, we'll have 3 sections. First, we'll get to some of the beginnings, the Principia and some of its friends. Then we'll move on to cross-modal VLMs, so more of the kind of modern stuff, where modern means last 2 years, and beginnings means 3 years ago. And then at the end, we'll talk about various applications of these things in industry, in research, and I'll just give a brief outlook and talk about what excites me in this area and what I really look forward to seeing in the future. Cool. Okay, let's start with the start. So it's a broad topic. A good place to begin is sort of a definition. So what is a vision language model? A vision language model is any model that learns from images and text simultaneously, so takes both of these modalities and input, and produces, in this talk, we will restrict ourselves just to text. So there are VLMs that can also produce images, but for the purposes of this talk, we'll just look at those models producing text. And with this text, they can obviously solve many different tasks, including image classification, but also vision question answering, different captioning, entailments, grounding, all sorts of various things. So as you can see, it's a broad field. This is a very broad definition. So we'll cram a lot into all of that. And just to kind of give you a very initial orienteering around that, there are a few things that you should consider when you're thinking about vision language models. So there are a lot of design choices you can make in this black box when text and image come in and text comes out. So some of these design choices are obviously, how do you encode these 2 different modalities? So there are different modalities. Should you be using similar architectures, very different architectures, and bigger, smaller, lots of these questions. How and when do you combine these modalities, right? If you have two things coming in, one thing coming out, you have to somehow combine them. Do you combine them early on, later on, or at the very, very end? What losses do you use to train these models? 1 loss, 2 losses? Are you thinking something like contrastive learning, image-text matching, masked language modeling, all things we'll talk about later? Or, captioning, or even more? Should you train from scratch? Or should you use pre-trained models? Since so many of these models, or so many of unimodal encoders, image and text only, are available online, should you start there? Or should you venture into the training realm and try to burn some GPU hours? And very important, although listed last here, is what type of data should you be using? Are you going to go for paired data, image-text pairs, interleaved data, or could you even be using some unpaired data? So as you see, many questions. even more answers to all of that. So I was definitely mind blown when I started working in this area, just by the sheer amount of information and, in general, things you had to learn. So I will try to now introduce you gently. So we'll start on easy mode. Don't worry about all the complexity. And specifically, we will start with dual encoders. So what are dual encoders? Well, let's take our image and text. This is a paired example. And we now encode them separately. We use a specialized image encoder, a specialized text encoder. And we only combine them at the very end. So every modality has a single dedicated encoder. We have the modalities only interacting at a loss, so only the final outputs of these encoders will be interacting. And here, I will first initially focus on training these models from scratch. So you randomly initialize the networks, and we will train them simultaneously, so in a single training stage. And we'll focus on these models for now, because I want you to see how you can really go from zero to a trained model. And you will later, also in the tutorial, see some of these models. Okay, so before I dive into describing some of the methodologies and models, I just want to quickly talk a bit about history. So the story of the models that we will explore today begins in January 21. So this is meager 3.5 years ago. And at that point, there were two very significant papers. CLIP, I'm sure many of you have heard of, and Align, which is a concurrent work and is a very, very similar model. CLIP came from OpenAI, Align came from Google. So for the rest of the talk, I'll focus on the CLIP model, as it's just a bit more well-known. You also can find these checkpoints on open source. You can use them through Hugging Face and other methods. And for also ease of explanation, go through there. But just to tell you, all of this also is very closely aligned with the Align model. And at the very end, I'll show you some very cool results from the Align paper. Okay, so CLIP, or connecting images with text. This was a really big turning point. So in January 21, I remember being really amazed by the simplicity, but by the power of the method. And that kind of sparked my interest in VLMs. I was at that point working mostly in computer vision, especially representation learning, self-supervised learning. And at that point, I thought, okay, I should really pay attention to this VLM space. There seems to be something really exciting happening there. The interesting thing with CLIP is that in one very nicely written paper, so if you haven't read it, I encourage you to do that, they introduced a few innovations, a few simple things that were at that point, in hindsight, extremely clear, but at that point were unusual for the field. And in addition, they open sourced the models pretty quickly, so the models could be used by the community. And that really created a big revolution in the field. So what is CLIP about? Well, we're dealing with VLMs. We're in a dual encoder setup. So we have, good, it works. Okay, so we have images and the associated text. So we have paired data. We have those coming into the specialized text encoder and a specialized image encoder. And these encoders are producing single vector embeddings of the corresponding images. And so what we then want to do is we want to compare images and texts within a batch and learn representations based on these comparisons. So how are we going to compare those? That's the main question. And again, also, how does training proceed in these models? So one big innovation with CLIP was they put a lot of effort in curating a large data set. So They curated the web-scraped pairs of images and text and got to around 400 million pairs. And this was a really, really large scale at that point. Now we're talking about billions and billions, but at that point, 400 million was really unprecedented. And their motivation for this was that by having this large scale, they will have a lot of variety, a lot of complexity in the data. They might have some noise because they were web scraping. The data sets were not carefully curated like, say, ImageNet. But they could trade off this noise for the additional scale that they get. Then one simple idea was, okay, how do we compare the images to the text? Well, we can classify which caption belongs to which image. And we'll dive now, we'll in a bit dive a bit deeper of how this classification is actually done. We learn both encoders from scratch, and because of the way we do this learning, we're also working with very large batch sizes, which kind of also goes hand in hand with the very large data that we have. Okay, so how do we learn to classify this? We use contrastive learning. And so I'll just now briefly talk 3 slides about this on a very, very high level, and then come back to CLIP and apply this there. So, okay, what is the general principle? The general principle is we have 2 views of one data point. So imagine for an image that might be 2 different augmentations of an image. And we learn a representation so that we maximize the similarity between 2 views of this single data point. So we want them to be as similar as possible, while at the same time minimizing the similarity of that data point with the rest of the batch. So kind of imagine in a latent space, you're pulling 2 vectors together and pushing away 1 vector and the rest of the batch. Okay, so just a visual description of this. This is the example when we have images. So just in image space, we have 2 augmentations of this polar bear. We put them through the same encoder. We get embeddings, and then we compare those embeddings with the rest of the batch, calculate some scores, and then have a cross-entropy loss on top of that. And CLIP, in general, draws a lot of inspiration for its work from the contrastive learning self-supervised literature. Okay, so some scary math, which I hope won't be scary in a moment, or is not scary at all, which would be great. So the contrastive loss, what is it in terms of the math? We are looking at all positive pairs. We are then sampling our negatives from the rest of the data set. In our case, when we implement this will be the rest of the batch. And then we're looking at the negative log of this particular fraction, which is computing the similarity scores. And so the similarity scores of fx transposed with fx, the positive pair, and then we just normalize using the exp trick. Okay, so what does this correspond to in the original image? Well, the numerator, this is where we are maximizing the similarity. This is where we take those 2 embeddings of the 2 augmentations, push them through the encoder F, get the final embeddings, and then try to maximize this similarity. And here in the numerator, you again have this term, so this stuff sums up to 1 nicely, but you also have these negatives, where we are minimizing the similarity. Okay. Now, this is actually a very straightforward objective, I would say. There are a few things to consider, though, when you're implementing this. And so there are some tricks of the trade, which are usually explained in the papers, but I'll just briefly mention them here. So usually, these embeddings, you would L2 normalize them, so to have unit norm. The parameter here, this temperature, is also incredibly important. It's a very important hyperparameter that you usually spend a lot of time searching over, which is a good value, and so on. And the very important thing is, because you are trying to maximize similarity to something which is already very similar, you have to have good negatives. Especially, you have to have a lot of negatives. So you end up having these large batches. And if you look at this objective carefully, you realize that for every data point, to compute the loss, you actually have to have the whole batch on the device, which puts significant strain on the memory that you have. So that depending on which architecture and which accelerator you have, you might be limited by the batch size you can have. Also, one important thing to remember is that this objective is not symmetric in the way it is written here. So if you look at augmentation 1, take this as your original point, augmentation 2 as your positive. You also have to do it the other way around. So take augmentation 2 as the original, and then compute this objective for augmentation 1. So usually you would have 2 loss terms. And remember this as we move on back to CLIP. So remember, oh yes, please.
I've always wondered why you need to minimize the similarity between the whole batch. So does this come from theoretical consideration, or is it more of an empirical thing that what's written?
That's a very good question. I'll just repeat it briefly for the rest of the room. The question was whether you have to minimize with respect to the rest of the batch, the whole rest of the batch. The answer is no, you don't have to. And there is a lot of literature on how do you pick good points, good negatives that you want to minimize the similarity on. Like this is like a whole small sub-area. I would honestly say from my own experience, negatives, although the literature puts a lot of emphasis on that, are far less important for the representation that you learn if you can get better positives. So if you want to spend your effort somewhere, spend it in finding better positives, more positives, not just augmentations, but actually semantically similar things. And negatives, one trick we found worked really well was actually to subsample the batch. Because in the batch, you might actually have things that you don't want to be maximally dissimilar, but are somewhat similar, so you don't want to push them fully away. Okay. Returning back to CLIP, so remember we want to classify which image and which caption belong together, and we've just learned about the contrastive loss. So we're gonna now use 2 views of the data as the image being one view of the data, and the text, the associated caption, being the other view of the data. So we're gonna have an image to text, contrastive loss, where we're trying to maximize the similarity of an image with its associated caption, and then also minimize that image embedding with all the other captions from the batch. Also, to symmetrize the loss, we also have a text-to-image contrastive loss. And so the final loss is actually a summation of these two. In the text-to-image loss, we're doing the opposite. For a fixed text, we want to maximize the similarity to its associated image, while minimize the similarity to all the other images in the batch. Okay, so this is just a very brief description of what does, apart from the math, what happens in the embedding space. So again, our picture of the wave, now a bit more complex text. So we're pulling these together in the joint embedding space. And this is one really important key. I think that I definitely didn't realize the first time I read the paper, but thinking back is actually really, really interesting, is the basis for a lot of stuff that happened afterwards. So this embedding space is joint. So we have both image embeddings and text embeddings living together there, and it has a shared similarity metric. So we can kind of think as having access to the visual space through text and having access to the language space through visual inputs. Okay. Now, why is this important? This is important because this now opens a whole new area of research. And this is one of the really exciting bits, which is this enables us to do a lot of what is called open vocabulary. A lot of computer vision, you would usually say for classification. You would have a set of predefined classes that you train on, and then you can predict these 100 classes that you trained on. But imagine if suddenly at test time or during deployment, you want to, add you found 10 new classes and you really would want to have your prediction of the model on these 10 classes. Well, guess what? You would have to readjust either your full model or at least parts of the model to enable this. And having this joint embedding space actually allows us to not have to do that, because we can just embed things and compute a similarity, right? We have some new classes, there's a text, we just embed that text and look at how similar it is with a particular image. And this is what CLIP did. CLIP did open vocabulary classification. So let's say you train your model, and then you have a new image, and you're wondering which class does this image belong to. And so what you do is you take all the candidate classes, you embed them, and then you look at the similarity of the image embedding with those text embeddings. And for your prediction, you pick the highest scoring one. Okay, now, obviously, you have to pick which classes you want to use. You want to create this prompt. And depending on which classes you pick, how you construct a prompt, you might get different results. So, welcome to prompt engineering. Prompt engineering is very important from CLIP onwards until now. And so, a surprising amount of work really goes into prompt engineering, not just model training, although you would want this to be a bit different. But yeah, prompt engineering, very, very important. So first, it bridges the gap from the training distribution to the current test distribution. And it also provides context. So especially when you have certain situations where you might have ambiguity from a single word, like a boxer. Is this a human, or is this the boxer, the dog? And so you might, with a prompt, with a full caption, give a bit more context for the model to disambiguate. Just a quick note from the paper. So on image top 1 accuracy, you get 5% with prompt engineering, and 5% is huge. This is huge. Like you could probably publish, 5 papers with 1% improvements, and in one paper you get 5% improvement. And of course, for the best performance, you want to be customizing the prompts that you get. So prompt engineering is very important, and it is actually a skill. So if ever in doubt, yeah. Cool. Yeah. Just before we wrap up this section, just a brief, very cool application of this joint embedding space. And that is this zero-shot retrieval. So let's say you want to look up some Van Gogh images. And you have this caption, Van Gogh, Starry Night, details. If you add details here, you would retrieve this image, right? Remember, it's a shared embedding space. So we just embed a caption and get the nearest neighbor from all the images. If you change now to Van Gogh Starry Night in black and white, you would get a different embedding, and you would get a different nearest neighbor. And the very nice thing is, actually, these images do correspond. Like, there is semantic similarity between the text embedding and the actual image. And you can do this very nicely. Here, actually, is a very, very cool thing. Seagull in front of Golden Gate Bridge. It gets you that bridge. This is London Tower Bridge. Again, a seagull and the bridge. Sydney Harbour, and this is Rialto Bridge. So you can, in a way, transverse this joint space, either by looking at the vision side or at the language side. Who was for,
Yeah, so my question would be, when you're saying retrieve, does it actually, like, do you have the set of images that you unfold and see the differences between the content images? Or you actually, as you said, like, traverse the space somehow and just take the latest and you follow? Do we have the choices of images or not?
So the question was whether we are retrieving within a fixed set or the generalized set, I guess. We would be retrieving within a fixed set.
Right. So if you don't have this photo of seagulls, we don't magically just find the close one and like trace it to them. That would be too quick, right?
Yeah. So if the image is not in the space that we're searching over, we would not find it. You could imagine something if you had if you would train a decoding model that it would generate this sort of image based on this, but in this particular case, we would not have this access to that. And so depending also, and I think this is also a very good question, and just let me make this point that if you have a set over which you're retrieving, which is very complex in a sense that it has very small details. Depending on whether your model is able to differentiate these details, you might not get such good separation.
That would be my another question is, do you think to separate across human appearances? Like, is that the small enough difference you're talking about? Or is it a valid, concept that it could differentiate?
So whether it would differentiate on human appearances, the answer to that would be it all depends what you have in your training data. So if you have data which has these small differences in human appearance during training, it could. But otherwise, probably it would be rather difficult. There was another question?
Yeah, same question.
Okay, same question. Any other question from this side of the room? Okay, next time. Okay, and this one I also found really cool, and that is because you have an joint embedding space, what you can do is obviously with vectors is add and subtract. So you can start from this image, let's say of a panda, and add the word red, right? Embed them both in the space, add those two vectors together, and look at, again, the nearest neighbor, what is retrieved. And this is, I think, a red panda bear, but I might be wrong, but definitely looks reasonable. This one also with the high heels, changing colors is pretty neat. So you can do this sort of vector arithmetic and look at where you end up, what is the closest point to your new vector. And the really interesting thing is actually that this embedding space does encode some semantics. Although you can imagine, like you scraped some images from the web, might be very noisy, how can you really disentangle these things? Well, it turns out you can disentangle some of these things. Okay, so quick summary, wins, big win. Like CLIP really jump-started a revolution in the field. It was a new paradigm for training and evaluation of visual representations using language. It was simple, the model, the objective is also rather simple to implement. We had these unimodal representations in a shared space. CLIP showed how to do open vocabulary classification, which then enabled a lot of the community to do open vocabulary something else, open vocabulary detection, open vocabulary segmentation, and many, many other things. And CLIP really showed the power of large data sets to the community and showed also this trade-off between scale, variety, and complexity, and noise. So you can actually get away with having some noise in the data as long as you have sufficient scale. Now, obviously, there are some challenges. We have scene level alignment. So we're looking at the whole image, comparing it to the whole caption, right? We have only one single vector, embedding vector. And so some of the granularity in the caption might be just lost in learning. Also, the way we're learning things is we're looking at averages, so that you have a kind of like, think of an average of the image and an average of the caption, which then loses obviously the 2D structure of the image and also loses the ordering of the caption, the ordering of the words of the caption. So some granularity is lost. And so some of the fine-grained details in an image, for example, in a complex scene, you just might not have that in your representation. The other thing is that we need paired data. So we need image-text pairs to be training on this. But there is obviously much more unpaired data. There are many more just images without associated or good captions, and there is a lot of text on the web that you can easily scrape. The contrastive loss obviously requires the whole batch, and prompt engineering is important. Okay, so CLIP was January 21, and this both was a revolution in terms of the way they used some things, but also created significant interest in the community. And even to this day, there is a lot of ongoing work in improving CLIP or using CLIP for various different tasks. And so here I'll just talk about a couple that I want to highlight, and then we can go from there. So the first thing that I mentioned was this scene level alignment between vision and language. So you're just looking at an average of an image, the average of the text, and fine-grained details might be lost. There have been a lot of, even from 21 onwards, a lot of papers which try to do this improve the fine-grainedness of the information in the representations. A lot of these methods, unfortunately, usually do this at the expense of scalability, so coming up with very complex objectives, and just being even less scalable in the contrastive loss to begin with, when you want the best performance, you have to get the biggest batch sizes, and then memory really becomes an issue. And this is some work that I did with some colleagues from DeepMind, including Jovana and Anastasia, who will hold the VLM tutorial just after this. So feel free also to ask them, but I hope to give an introduction here. So the shortcoming was scene level representations, and we don't learn an association between parts of the image and parts of the text. So think of, say, like a meadow, a dog, and a cat playing there, and that being the associated caption. So what you would preferably want to do is take that word dog and have a region of the image that corresponds to that. Same for cat or for meadow. And so this really was the key insight we had. But before that, just to show you that indeed, the scene level representation that CLIP is learning, if you look here at effectively a heat map, or let's call it a CLIP attention, where we're looking at where CLIP attends for the word cat, while CLIP correctly would classify all these three images as cats, for this particular image, looks kind of a bit all around, a bit on the cat. Here, again, the attention is very scattered. And here, it seems that it's looking more around the cat than actually at the cat. And so our key idea for this work, Sparc, was that for every language token, so think of it as a language token corresponding to a single word. Depending on tokenizer, this is roughly correct, but just think of a single word. So for every language token, we learn a weighted combination of associated vision patches. So we're really learning which vision tokens and how much they correspond to individual words in the caption. And through this learning objective, we are aligning those two spaces even more closely. And this weighted average we call language grouped vision embeddings. And just very shameless plug. If you're going to Vienna next week for ICML, please do check out the poster. This work is being presented there. But okay, cool. So remember the contrastive loss, and I was telling you that we're looking at these averages of the images and the text. Peel one layer of the encoder back. Before we average this, we have embeddings of, on the language side, individual tokens, and on the vision side, individual image patches. And we'll call them token embeddings and patch embeddings. So these token embeddings are literally the embedding, the not the final, but the one before the final layer of represents that vector of these individual tokens. And same for image patches. Think of these embeddings. And so what we want to do now, obviously, if we want to learn which image patches correspond to which token, is we have to compare them. So we have to compare the cat or let's take here the dog, we have to compare how much this vector from the word embedding corresponds to individual vision patches. And here we have with different colors associated higher similarity, or like white is no similarity. And based on this similarity, what we do is we create a new vision embedding. So we take the similarities, we take the vision embeddings themselves, and then create this higher level, this weighted average, which now takes the place of the average of the whole image. And we do this for every token. And now what we do is we compare this weighted vision embedding with, so this weighted vision embedding, we compare with the associated language embedding. So that we are now pushing those two things together in the joint embedding space. Here, also just to note, we still have the global contrastive loss, so we're still looking at learning global information about the whole scene, in addition to having this local information that associates words with part of the image. Okay, and indeed, we set out to have better fine-grained alignment, and this is what actually happens, so hooray. If we look now here, these are some zero-shot segmentations of, say, here, this horse. This is the ground truth of what a segmentation mask looks like. This is what Sparc discovers, what it thinks the horse looks like, where it is in the image, while a competing method and clip kind of spread the attention all around. Like, yes, the horse is somewhere in this image, we know that, but only Sparc is able to really localize that. And you can see this also for this motorcycle image. Depending on this one I found really cool. Like, it really discovers the different parts of the different pots. So, yeah. Yes?
So you need to have that segmentation mask trained. How you associate patches with both.
So the question was, do we need segmentation masks to train the model? No. So the ground truth, there is no ground truth, right? So what we're doing is we have the global contrastive loss, and we are here just looking at the similarity of this token with this vision embedding. So that, and remember, right, we have some signal coming from the global loss, and so these embeddings won't be fully orthogonal, right? So there will already be, think of it as there will already be some initial small similarity, which makes these patches more similar than this patch. And also we use a trick, which is we explicitly enforce sparsity. So while with every of the patches, this embedding will have some similarity, right? The similarity is between -1 and 1. What we do is we cap and we say like only 10% of the image patches can be similar to each word. So that then we say like, okay, pick the 10% of the most similar, and that use as representation. That trick really, it's a lot about computation efficiency, but also it does improve the representation, so that you're actually, you just need a small spark to start the learning, and then you can also narrow it down with the sparsity.
How big are the patches in practice?
Depends on the architecture. Okay. Just in the interest of time, okay.
Did you run any calculations on the size of the patch that best performs on this kind of approach?
So in this particular paper, we looked at vision transformers, and we looked at sizes of 14 and 16.
Did it help to go lower resolutions? I mean, less pixels in the image patch?
In general, yes. So especially for, yes, it is more computational intensive, yes.
But the words and in, they don't
Yeah.
They don't have initially alignment with the
That is true. We didn't do anything specific about that because we found this was not a big issue in the learning. So even just leaving those stop words was fine. So we don't start from any pre-trained network. We start from scratch, so from randomly initialized networks. And we have both the global contrastive loss and the local contrastive loss. So these two signals are feeding off one another. But I think this also, this merits more of time, and just because I'm running out of time, let's take this offline. But please find me after the talk. Happy to answer this question. Okay, just very. Okay. So just briefly, this was an extension of CLIP, but I also want to briefly talk about these open vocabulary models, and there. This paradigm of shared image text embedding, which hopefully I've repeated now 20 times, so you will take one thing away from this talk. It also created an explosion in computer vision models tackling open vocabulary tasks, like open vocabulary detecting, so predicting bounding boxes of not seen classes during training, and also segmentation, and many more. Here, I'll just highlight very briefly two of these methods. So one that that was developed at Google, it's this ALVIT model from 2022 from some of our colleagues that we also, that is really a good detector to begin with. I think it's also available open source through Hugging Face, so check that out. And this other detector that I found really cool. So this is YOLO. YOLO is a you only look once detector. So it's usually for like devices and just more efficient in general. Okay. Okay. And what you saw there in this brief clip was real-time open vocabulary detection, where they used a clip text encoder to get these semantic embeddings and then trained a separate YOLO encoder to do this real-time detection. And it's pretty fascinating how well it works. And the point is, open vocabulary, you can, on stuff that the YOLO detector wasn't trained, you can just embed it with clip text encoder and go from there. And you see the model being able real-time to detect that, which is quite impressive. Okay, so this is the basics wrapped up. Let's go over now to some more modern stuff, cross-modal VLMs. Cross-modal VLMs, it's what you imagine, right? You have image encoder, text encoder. You might have a loss between those, as you did in a dual encoder setup, but then you have usually a multimodal text decoder that also has an associated text loss, usually, on top of that. And the general idea with this is that having a multimodal model, this cross-modal encoder, allows for more complex interactions between the images in the text. Because in a dual encoder setup, we had only interaction at the very end through the loss, and we only had interaction of the representations that were most abstract. And so having a cross-modal encoder allows us to have interactions also on lower levels and to then have more fine-grained image text understanding and be able to tackle more complex image and multimodal tasks. So here I'll just talk about some methods, and this is a very small subset, some which I think particularly are important for the field and some which I like. And just, if you thought CLIP, there were so many, well, there are a lot of variants of CLIP. There are also a lot of variants of cross-modal VLMs that it's our own sorts of like sub-area in the vision community. One, which is quite interesting, is the Coca model, or contrastive captioners. This came out in, I think, 2022, and was a very, very simple idea of the cross-modal VLM. So take the contrastive learning that you had between the unimodal text and image embeddings, add a captioning loss that comes from the multimodal encoder, and predict the caption word by word, token by token. Now, what is the idea here? The idea is that you are, while you're encoding these two modalities separately to begin with, you are mixing them later on. So you are taking the image, and these are the image patch embeddings. These image patch embeddings are cross-attending into the text decoder, which takes in takes in text tokens. And then you're predicting the caption. And with that, you're enabling the vision image patches and the text patches to align themselves within that decoder. Just in the interest of time, here the math, here's the math. So just very briefly here, in the captioning loss, you're predicting the next token based on all the previous tokens and the full image embedding given through the image patches. One interesting thing also with this Coca was that it was one of the first foundation models in this space. Not the first one, but one of the first ones, where you train your initial model, and then you can take parts of that model, either the image encoder or both image and text encoder, or take the full model and perform different tasks. Classification, some alignment, for example, using retrieval using alignment, or image captioning, or even some more complex things like entailment or grounding. What this allows you then is to have one training procedure, but then a downstream model which works across many, many things. And this is what they nicely showed in this, I think, spider plot, where you have going from classification, image classification. Kinetics is classification from videos of human actions, and then there's image text understanding. This is visual question answering. This is captioning. So on a lot of different, very different tasks, classification and visual question answering are obviously very, very different, but they can be cast in the same light through text and interfacing text with vision. You have really good performance across the board. Okay, so Coca was one of the first foundation models, and just to also note here, Coca trained everything from scratch. So this was massively computationally expensive, training everything from scratch, and we will then later on see how this changed in the field, and even changed today. So Coca, I find this work very simple. Like the idea is take a contrastive loss, add one additional loss, just a captioner, add just a decoder, and off you go. Train everything from scratch. If it works, it just works. And this is just as an example, as also a very popular method. But I think one thing to consider when you're in generally building your own models or training models, it is very easy to add a lot of complexity really quickly. A lot of complexity usually means a lot of training problems, instability, or just bugs that can creep up in your implementation. Just to highlight, this is a good model. Just want to highlight how quickly things can become very complicated. So we have, again, a contrastive loss, and then the paper proposes to sample some hard negatives for this image text matching loss, where we're looking at a binary classification problem from an embedding which combines image and text features. Then, we have a third loss, which is masked language modeling, where we're dropping certain parts of the caption, changing it to a specific mask token that then gets predicted. And on top of that, to squeeze out more performance, we add a whole momentum model, which is basically this model, but an exponential moving average, and then do all sorts of kind of things. But you can get a lot of really good performance out of these models. But this again, just beware as you're scaling things up, as complexity increases, you are making certain trade-offs. And I would say one thing which is good to have in mind with VLMs is that you can trade a lot of complexity in the model or trade it away with scaling up the data, with spending more time on the data curation and data gathering process. So if you can, invest your time in gathering 10x more data, or spending time in putting in, ideas of how to change architectures, I would definitely go for the former. Okay, so I mentioned training these models is very costly. So we do have from, the computer vision community and that point also the language modeling community, a lot of pre-trained models. So one model that takes advantage of this is the Pali model, which jointly both leverages pre-trained models and, very importantly, jointly scales them. So previously, in a lot of cases, you would not have the same number of parameters in the visual encoder and the language encoder, whereas with Pali, they again didn't have the same number of parameters, but they were trying to bring them closer together. So again, what is the motivation? Very compute intensive, but excellent performance. Can we amortize some of this computation with pre-trained models? And at this stage, there were also really a lot of models out there. This is 2023, so last year. Again, key idea is let's leverage these pre-trained models, and let's go for simple and modular design, but scale things up. Scale data, scale models, and spend time on that. The one interesting thing with this model is also that it's able to do a lot of different tasks without having access to any task-specific heads, which is quite interesting and quite powerful, honestly, because as long as you can specify a task through language, you can use this model without having to add anything. No classifier head, no detection head. You can just straight up use it. And you can even cast things like detection through language. And just very briefly on the model, what is the innovation? The innovation is we take a very big vision transformer for the image encoding side. The largest model they trained was 17 billion parameters in total for the full model, with the with the vision model making up 4 billion out of that. And it has been trained on a very large, I think 3 billion internal data set. Once you have your vision embeddings, very simple, you just mix them with your text and just let those two modalities mix. You add, of course, a lot of capacity on top of that, and then you have a text out. Just in the interest of time, so what you end up having is you take your pre-trained vision model, you take a pre-trained language model, you freeze the vision encoder, and you fine-tune effectively the language model. Because you're starting from pre-trained models, you can get away with not having 10 billion scale of training examples, but in this particular example, 1.6 billion. And the very interesting thing they did with the paper was that they focused on multilinguality. So they had over 100 languages, so a very long tail distribution. And that resulted in some very cool things, the model being able to do. So, start from, say, English, answer to you in Serbian. Okay, and here also, if you want your model to be able to perform a lot of downstream tasks, one good thing to do during training is obviously train it on these different tasks. But I said there are no heads, so the way they did this is to actually add specialized prompts, and through prompts specify which task it's currently doing. Yep. Okay. So just to wrap this up, some key findings. You want to jointly scale the vision and the language. That is important, especially if you're looking for multimodal performance. If you're just looking at language performance, that obviously is not important, but multimodal tasks really greatly benefit from scaling the vision encoder, especially if you're looking at fine-grained details. So not just scene-level things, but really having to localize parts of the image, having to answer how objects interact in the image, and so on. And yeah, again, complexity, shifting away from the architecture, shifting away from methodologies, and more into the training procedure, the data gathering procedure. Cool. Maybe just in the interest of time, I'll actually skip this and go on to applications and Outlook. And I just want to kind of briefly, when I was preparing the talk, I really thought, oh, well, I was looking up the dates and realized like, oh yeah, it's just been 3.5 years for all of this. And so I just want to highlight how much has happened in this rather short period of time. So in January, February 21, we had Clip and Align come out. So this was us being able to do open vocabulary classification, which is pretty basic, right? This is some very simple transfer learning. Then 21 was a very busy year in the community. Many different models came out, and end of 21 we had the LBEF model. Again, a lot of very interesting work. Flamingo, which I had to skip, happened in April 22. The Coca model in May. So we're just talking, a year and a half from when the revolution started, and 2 years ago. Then in June 22, GPT-3 happened. November, we had ChatGPT, and then we had Gemini come out December last year. And I think it is really fascinating to see how we've come from training on pairs of image text data, 400 million just scraped from the web, very little curation, just doing some classification, to now having the likes of Gemini, ChatGPT, GPT 4.0, being able to do a lot more than classification, a lot more. And that's, this really swift progress makes me excited to work in this area, and I hope I might have convinced you, or will convince you with the next few slides. So, I want to very briefly discuss some applications I found really interesting, and then close off. So one thing which is for me dear to my heart is VLMs for accessibility, especially for visually impaired people. So what you see here is Google Lookout app, which is an app helping visually impaired people navigate the world by, describing to them what is in front of them, where they're pointing the phone. And now Lookout is actually powered by Gemini, so that around, we can both do simple things by just recognizing individual items and having that spoken back to you. You can also do more complex things like objector OCR, or even scanning full documents and the model being able to hold a conversation about that document, because it can recognize the characters, and then with Gemini behind, it can also interact with you. Another thing which is really a field which is very nascent, but I think very exciting, is that of robotics, and combining robotics with VLMs, especially, for example, Gemini. Here, this is a video of a robot navigating the Google DeepMind office in California and interacting with the human.
Oh, hey, robot. Can you take me to a temporary desk?
Okay, thank you, Jovana. Please give me a minute.
I mean, it says, please give me a minute. Yeah, it's a bow tie.
Oh, thank you. How nice.
So the robot can also not just get language input, but also get language and vision input, and also perform some reasoning for navigation. I'll share the slides so you can look later. This one was really interesting because this one is actually really showcasing the models, the robot's reasoning, because it is. Okay. Yeah. Sorry. No, this one. This one is really. Okay. Let's write this off to a glitch. Okay.
Okay, thinking with Gemini. Please give me a minute. Ooh, I'm investigating if this place has your preferred liquid refreshment on hand. Stay tuned, friend.
This is very useful, by the way, when you don't want to get up. You can ask the robot to check. And hopefully the next feature will be free to grab it and bring it to you.
Based on the image, it appears that the user's favorite drink is Coca-Cola. The refrigerator in frame 1150 contains Coca-Cola. So you could respond to the user by saying, yes, they have Coca-Cola.
Good job, thank you.
So yeah, I think. And again, robotics is really an area which is just beginning. I think there are lots of very interesting challenges and lots of very interesting ways to combine robotics with VLMs. Yes. The spinning thing, that's most likely LiDAR. Another area, very interesting. Another question. It generally shouldn't be an issue for the largest models because you expect that you will have seen a lot of negation either just through the language modality or even through the visual modality. So I think it's, from what I've been testing, it's pretty good if you ask it, even, is this in an image? And it says like, no. So that it can definitely do. I mean, you could ask it, maybe like if it just predicts you there is a dog, you can ask it a follow-up question like, oh, is there something specific about this dog? I mean, depending, but you might need a follow-up, yeah.
Was the robot movement, so control also, was also controlled by the it's just like the process of getting from the desk, let's say, to the fridge was also controlled by the model.
That's a very good question. Was I guess Gemini in control also of predicting the actions to go forward, left, right? I would expect so, but I am not fully, because I would imagine so because it is processing the visual stream, and it would have to navigate around obstacles and so on. So that would be my like answer. Yeah. Cool. One very interesting area also, and very also nascent, so just coming up. This was a paper from this year, January, introducing this particular benchmark, the visual web arena, is VLM agents navigating autonomously or semi-autonomously navigating the web and performing certain tasks. So these are two examples from that particular data set, evaluation benchmark. Say you have a task where you want to buy the cheapest color photo printer and you want to send it to Emily's place. Now, you obviously could type in, oh, this is Emily's address and so on, or you can take just a picture like, oh, here is Emily's address. And so the model would have to understand the picture, parse it, find the address, and then also go and navigate through the web page to execute the tasks. So here, this is just a very short excerpt of an agent navigating through the web page, where it goes through things, puts stuff in the checkout, fills out then based on Emily's address where it should be sent to, and then places the order. Another interesting, and I think here we're really only limited by what we, I would say, at the moment can think of. How would you evaluate these models, I think, is also a very interesting part of the research, not just what the current models can be doing. Because given how good the generalizations these models are, given the large training corpus, you can ask it very, very interesting things. You can underspecify a lot of things through language, give it only through vision, have the model infer things on the fly. So this is, for example, a task where it asks to add to the shopping cart all the items so that you can connect these two things without specifying what these two things are, right? So this is a MacBook and this is an Ethernet cable. And again, you know, the VLM, what it should be doing is getting those images, understanding what's in the images, combining this with a task, text, reasoning what to do based on this. And then we have the agentic part, which is then predicting and executing actions. So having the web as its environment. Okay, this is just a short video of that. Okay, so as we are running out of time, I want to close this with what I found really exciting is how VLMs can be deployed in real time, in real life. And for that, let's quickly look at this short video from Project Astra, which is an internal project at DeepMind.
Okay, let's do some tests. Tell me when you see something that makes sound. I see a speaker, which makes sound. What is that part of the speaker called? That is the tweeter. It produces high-frequency sounds. Give me a creative alliteration about these. Creative crayons color cheerfully. They certainly craft colorful creations. What does that part of the code do? This code defines encryption and decryption functions. It seems to use AES-CPC encryption to encode and decode data based on a key and an initialization vector, ID. neighborhood do you think I'm in? This appears to be the King's Cross area of London. It is known for its railway station and transportation connections. Do you remember where you saw my glasses? Yes, I do. Your glasses were on the desk near a red apple. What can I add here to make this system faster? Adding a cache between the server and database could improve speed. What does this remind you of? Schrodinger's cat. Alright, give me a band name for this duo. Golden Stripes. Nice. Thanks, Shannon.
So this is all. This is. I was actually going to say this is all done with one single model. This is all done with one single model, and you saw many, many different tasks and many different scenarios where the model is able to eloquently answer that. This was all real time and single take. And with that, thank you very much for listening.
Thanks very much, Jovana. That was very exciting, as expected. I think we have time maybe for one or two questions from the audience, and then we'll take a break.
So you mentioned that when you train, like for example, the model, you get the vision embedding and the text embedding in the same space, right? And I guess aside from that allowing you to combine those two types of information and getting relationships, that also kind of creates the embedding space might have more information, like more semantic information about different modalities, right? And so I was wondering if that allows you to create like a space that has more information that you could get from just one modality, and like if that allows you to have better performance even in unimodal tasks.
So I would say it depends what tasks you're looking at. If you're looking at, I think there are also different trade-offs to consider, because with this approach, the image text learning, and the contrastive approach to that, you're able to take advantage of not so clean data, for example. And while, you know, for a segmentation model, let's say, you might want to actually have very clean data if you want the highest possible segmentation performance. Especially if you're looking at something like closed vocabulary segmentation when you're testing and training on the same set of classes. So I would say, in general, does this approach beat out specialized unimodal models? Probably not, on average, but there are definitely scenarios where you can benefit from a lot of information transfer, knowledge transfer from the noisy image text domain, and then have your network already in a reasonable part of the parameter space where you can then leverage a smaller amount of additional data specialized to that thing. But if you're looking for very, very specific niche things, for example, you know, say some very specific approach to monocular depth estimation, you probably are still better off, you know, going for that specialized model with that specialized architecture, pushing performance on that. But if you're looking for models which are generally applicable to not just a single, very limited task, you might want to go a more general route.
One more question.
Yes?
At some point, it seemed that
So one approach to this is having very large context lengths, so where the model has access to a lot of information to make the next prediction. So, for example, I think the latest Gemini 1.5 models, they have over a million token context length. So this is in tokens, right? So that video you would have to tokenize in a particular way, probably dropping out some frames and so on. And you probably could fit, depending on how you do it, maybe even like a full minute of video into the context, and maybe even more for the model to reason about. So it's all about the memory being what you let the model access as history before it makes the next prediction.
Right.
Yes?
Oh, yeah, we can take one more.
Yeah.
Go ahead.
Yeah, so we saw that it has multiplicity in text regions, so it can easily be used to actions. So my question is, how can we add actions to this as well? And how could we, obviously there are models that can do that, but how could we effectively add actions to this space?
That's very good. That's a very good question, and it's a very active research area. So I would encourage you to, yeah.
All right, let's thank Jovana again.